It's kind of okay, but draw big, I guess. Okay. Okay, so I guess I could start, right?
Thank you very much for participating in this workshop. Originally, I had no plan of a workshop for this year, but in this month of July, I'm having 6 visitors from abroad. I also have 7 students and former students. So all of us were curious about each other's new results. So we decided to have an informal workshop to hear about each other's new results. So we made that decision only 3 weeks ago. Okay. So our first speaker for this workshop is Meeks. We will talk about his brand new results.
Right. Okay. Well, I would strongly suggest everyone have a copy of this, right? So you could think of this as something you can look at later on. And when I'm going to introduce a lot of these things on the blackboard or on the slides. And can you hear? Is the speaker working? Is this working? The microphone? I don't hear anything. What?
Yeah.
You can hear the microphone's working?
Yeah.
Okay. Okay. So I strongly suggest to take a look at this. These are pretty much all the slides I'm giving here. I probably won't give all of these. So the first part of my material is about semi-direct products, Lie groups which are semi-direct products of R2 and R. And so I'm going to talk a little bit about that first. And they form a large collection of the homogeneous 3 manifolds. So if you take a 3-dimensional Lie group and you take what's called a left invariant metric on it, then you get a homogeneous 3 manifold. And anyway, so if you're looking at simply connected homogeneous 3 manifolds, then you get essentially all of the homogeneous 3 manifolds by taking a Lie group with a left invariant metric. All of the homogeneous 3 manifolds except for S2 cross R. So this is essentially modular one particular example. These are essentially all of the Lie groups. And like I say, about half of them were called semi-direct products. All right. Anyway, there are lots of interesting ones also, of course. So I don't know if you can see this. When you have a semi-direct product of 2 groups, let me just turn this light on. You have a general H semi-direct product V, and we have a little sigma here. So the sigma tells you how to do the group operation. Okay, so you can think of this as point set as the cross product of these 2 groups, and then you want to sort of change the multiplication by a homomorphism sigma. So in other words, this group is going to interact with that group by the sigma. So in most of the cases we're looking at our H, which is, think of it as a horizontal group, okay? So think of it as like a horizontal plane. H is sort of the xy plane. And we have the V, which is like the z-axis. So that's the kind of a picture you want to kind of keep in mind. So we have the horizontal and we have the vertical. So to define the multiplication, we need a homomorphism from the vertical into the automorphisms of R2. And you can just think of this as like GL to R, okay? Linear automorphisms of that group. Okay, all right, so how do you do that? Once you get that homomorphism sigma, then you define the group operation on the semi-direct product by star, and what you do is, the second part is very simple, you just add. So in this picture you add the z-coordinates. But the first one has this interesting interaction with the second group. The first coordinate is the first coordinate, and then you take this homomorphism, you apply it to P1, and then that's an element of the general linear group, and then you applied it to P2. So that's the way you do group operation on a semi-direct product. Okay? So yes, another interesting thing is in the sort of classical situation where we have R2 here and R here, any homomorphism from R into automorphisms here is always given by exponentiating a matrix. So this is always given by e to the t a. Okay, so in other words, and this is just means summation t to the n, a to the n over n factorial. So you just use your usual summation of exponential notation. So we're going to use this notation here. So in other words, instead of writing sigma, we're going to write an A, which determines what sigma is. Okay, so just some simple examples. Right. So, I should say something about how you get a metric on the Lie group. Okay, so we have this sort of like a cross product, the semi-direct product given by A. The metric on here is we want to take a inner product as the identity element, and so we just take the usual inner product here. So you think we have the xy plane, and we have R. This is just R3. So we have sort of standard basis elements, parseback to x, parseback to y, parseback to z. We declare those to be orthonormal, and then we extend those by the group operation to left invariant vector fields, and then do some metric on the entire group. Okay, that's how we get the metric. So this semi-direct product comes with a natural metric, which comes from the standard metric as identity element in this picture, right? We just take a standard basis here, E1, E2, E3, and then we extend that to our left invariant vector fields, and we just say that those vector fields are orthogonal and unit length. Okay, the simplest matrix to pick, of course, is just the zero matrix. If you exponentiate the zero matrix, you get the identity matrix. Okay, so this is just the identity matrix. So this is just our usual group operation. This is just the identity matrix applied to P2. So this is going to give you P1 plus P2, and we just get back the usual group operation. Okay, and the usual metric. Now, if you want to get hyperbolic 3 space, that's also an example of a semi-direct product. Okay. So we want to think of the hyperbolic 3 space now as being a Lie group with a left invariant metric that has constant negative curvature. So for doing that, you take the matrix to be the identity matrix. Okay, so I think you probably can see this, everything pretty okay here. So if you take A to be 1, 1, 0, 0. If you exponentiate this, you get e to the t. I probably put z, but anyway, put z. Z, e to the z, e to the z, 0, 0. So that's the way you end up multiplying. This is your sigma tells you how you do your multiplication. So if you take the identity matrix, then we get back hyperbolic 3 space when we take this semi-direct product. If we take this very simple matrix here, of course, when you exponentiate that, it's not hard to see. You can just do it by hand. You get this matrix. That tells you how to do the group operation. And if it's this matrix, we get the usual cross product metric on H2 cross R. So H2 cross R is, again, a Lie group with a left invariant metric. Okay? And it's the metric we get from this sort of procedure here. Okay, so right, so it's very handy. It's extremely handy if you have Mathematica, because you plug in a matrix, you plug it into Mathematica, it spits out exactly how you do the multiplication, and also spits out gives you back what the metric is, what the left invariant vector fields are, what the right invariant vector fields are, and so forth. Okay, so let's just do some more examples. These are more interesting examples. We can recover what's called the Euclidean group this way. We can recover Sol, and we can recover nil. So this matrix looks like a rotation by 90 degrees. If you plug that into Mathematica, it's not hard to see you get this matrix. I mean, you could do it by hand almost, right? just think about it a little bit. You can just start computing. You see the power series you get. You can take, just plug it into that formula, for exponentiation. It's not hard to see you get this. And the related metric is a flat metric on somehow topologically R3, but we have a different group structure. So this is a flat metric on E2 tilde. Okay, if you take a different matrix, you can change this matrix, you still get E2 tilde, but then you get a not flat metric. Okay, so it depends on how you, as these matrices change, the metric and the groups in general change. Okay, if you take this matrix, again a very simple matrix, then we get back what the Lie group called Sol 3, and we have the usual metric on it. Okay, so if you exponentiate this, of course, it's pretty easy to see you're going to get that, right? It's just a diagonal matrix. It's pretty simple to understand how you get this matrix, and therefore you understand how you get the Lie group structure and so forth. Okay, another simple matrix is this one. Exponentiating it gives you this matrix, and you get back the group nil with its standard metric. There's really only one metric on nil up to homotheties, right? Okay, so that gives us back, shows you how a very simple way you get back all the information. Now I say all the information, I'm going to just leave this slide with you. It's probably the most useful slide if you want to do research in this topic, because it lists all the formulas. If you're given a matrix A, it gives you what we call the right invariant vector fields in terms of the matrix. It gives you the left invariant vector fields. Now these coefficients here are coming from exponentiating the matrix A. And it tells you how to find the metric in terms of the matrix. Okay, so that one slide is, if you want, as far as research in the subject goes, a big plus, right? To have this thing means that anybody can do basically any of the basic geometry in these semi-direct products, right? Just have very simple formulas. You can put them on one sheet of paper. You can write everything down, and you don't have to do the computations yourself. They've already been done somewhere else. Okay. All right. So just keep in mind you have this sort of nice table. I should say to get this sort of table was a consequence of some work I did with Joaquin Perez. So we have notes from a series of lectures I gave in Granada about a week ago, a couple of weeks ago. And as part of that course, we have notes where we derive all these formulas, okay, and other formulas, and show how to use them to prove theorems. Okay, now there are two kinds of Lie groups. This is sort of a dichotomy in structure for Lie groups. There are Lie groups which are called unimodular, and then there are Lie groups which are not unimodular, and those are called non-unimodular. So we have the unimodular ones and non-unimodular ones. The unimodular ones are the ones we see in, for example, Thurston geometries. If you want to make a compact quotient with a Lie group, take a Lie group with left invariant metric, and you want to take some discrete subgroup and have a compact quotient, then you end up having to always choose a unimodular group. Okay. Oh, that's not true. No, anyway, a lot of them are unimodular. That's what I just said wasn't true. Okay. Anyway, so to be unimodular means that if you look at this, LG is supposed to be the Lie algebra. And if you're given that left invariant vector field, if you take the Lie bracket with that left invariant vector field with another left invariant vector field, you get another left invariant vector field. So this add xy takes you from LG into LG by taking Lie bracket with x. That linear transformation has a trace. And the trace is 0. That's equivalent to being unimodular. It's probably the simplest definition. All right. Okay. Okay. So that's what a unimodular is. So be not unimodular means that this trace is non-zero. Its trace is non-zero. Okay. And so if you compose this with the trace, you get an onto actually map from LG into R. And so which is another Lie algebra. Okay, so anyway, if you look at the kernel of this add x, I'm sorry, look at the set of, you can do this on another level. Anyway, you look at a set of all x which have the property that the trace is always 0, then that turns out to be a two-dimensional subspace of the Lie algebra. Okay? If you're a unimodular, it's the whole space, but if you're non-unimodular, it's the subspace, and it's called the unimodular kernel. It's the kernel of some other map. So sort of x goes into automorphisms of x, certain automorphisms. So we have the unimodular kernel. Now hard to check that it's itself unimodular, and the only unimodular group of dimension 2 is R2. There's a one non-unimodular one, but the only unimodular one is R2. So this gives rise to a subalgebra which is commutative. All right. So we're talking about a theorem, and the theorem is telling us that if you want to understand this G, and you have on it a left invariant metric, then it's always described by a 2x2 matrix, and the group structure is R2 semi-direct product A of R, and the way you get this matrix is it's the matrix for this linear transformation here with respect to E3. So you find an orthonormal basis for this. E1 and E2 are a basis for so you pick so you pick a basis for this unimodular kernel. You pick a third vector which is perpendicular to of length 1, and and when you do that, you have this sort of related. This E3 gives you a non-trivial map from here to here, and it has a matrix, and that matrix has this form. So you do have to check, of course, that add E3 generally takes LG into LG, but it takes the unimodular kernel into itself. So it induces a linear transformation on that subspace, and it has a matrix A. Okay? How do you get the matrix, of course, is you apply the linear transformation to the basis, you get the first column of the matrix, you apply it to the second element, and you get the second column of the matrix. So it's all very, very standard, which tells us how to get all left invariant metrics on non-unimodular groups. They're nothing more than taking a particular matrix which gives rise to the group structure, and that matrix gives rise to a left invariant metric. So that's, if you want, a classification of how you get all left invariant metrics on all non-unimodular groups. In order to know you get a non-unimodular group, you need it's equivalent to the trace of this matrix is non-zero. Remember, the trace of the adjoint is going to be non-zero for non-unimodular, but it's going to be 0 for unimodular. So anyway, okay. So now, so the classification theorem is, so if you have a metric non-unimodular group, it can be expressed this way. With respect to a good basis for the unimodular kernel. Oh yes, so then we want to say, to what extent is it, how can we make this matrix standard? So kind of think of going the opposite direction. Suppose you have a G. We now know it can be expressed this way, but we want to pick a good basis for the unimodular kernel so that the matrix has a nice form, right? Make it more canonical. So a little thought, Milner figured out a nice way to write down the matrix. If you pick a good basis, then the matrix can be written this way. Of course, there's another thing that's done here to make it standard. We do a homothety of the metric. So remember that there's a matrix A. It has a trace. For a non-unimodular, the trace is non-zero. By changing the orientation in the Lie algebra, the trace is positive. By doing homothety of the metric, the trace is 2. Okay, so after doing a homothety of the metric, we can assume that the matrix has trace 2. So notice that's the way this is set up. 1 plus A, 1 minus A, so we have the trace being 2. And then if you pick, like say, the basis a nice way, then you get the matrix to look like this. And when you do this, then you have another nice property, that essentially the determinant of this matrix determines the group structure of the semi-direct product. Okay? So if you get this invariant called D of G, you just take the determinant of A. It characterizes the group G as long as the matrix is not the identity matrix. Remember, if you get the identity matrix, then we're in a very special case, hyperbolic 3-space. So except for D of G equal 1, this is a complete determinant, okay, of the group structure. Okay? And as long as you aren't the identity matrix, 1, okay, so determine the identity matrix certainly is 1, but if you don't have the identity matrix, then you get this other group. Okay? Okay, all right. All right, now what does a trace have to do with the geometry of this space? 1/2 the trace is the average curvature, in the sense of mean curvature. So, you know, you take the trace of A is the trace of the second fundamental form of the planes, the horizontal planes in this foliation you have. Remember the picture we had these planes? We have sort of an R2 cross R picture. So 1/2 the trace is the mean curvature. And another nice thing about this basis is this basis is a basis of principal Ricci curvature directions for the space. Okay? So if you look at these, they're left invariant vector fields. So they're defined orthonormal field at each point in space. And those are the Ricci principal curvature directions. And here's how you can calculate those values. So from this, you can calculate, for example, the curvature of any plane, if you know these. Okay, so that's a classification for, wait, so I'm still talking about this? Wait. I must have repeated this. No, oh, something else. What's going on here? Semi-direct products in general. I thought I read it right. So let G be a unimodular group. So now we want to look at the case when you're unimodular and you can express yourself as a semi-direct product. So non-unimodular, we had the matrix A having trace be 2 after we normalize things. In the unimodular case, we know the trace of A, which is somehow this adjoint map, is always 0. So the trace of this A is going to be 0. Again, we can find a nice orthonormal basis. Again, E1 and E2 are going to be somehow the basis, orthonormal basis for the R2 factor here. Okay, so in this case, the trace of A is 0, and so the planes in this sort of foliation we have here, the horizontal planes are all minimal. Okay. After scaling the metric on the Lie group, then you can express A uniquely as this. Again, remember, we're picking a nice basis for the R2 factor. Picking a nice basis E1, E2 for that factor. Then the matrix is very simple. So if you're in a unimodular case, you get these matrices. You have a plus, or you have the minus. Okay, or you have A has this form. Remember, this was the matrix that gives us back nil. Okay, so the determinant is -1. We get back Sol. We get all the left invariant metrics on Sol after a homothety. We're doing a homothety to make the determinant be -1. Or we get determinant +1, and then we get the group E2 tilde with all of its left invariant metrics. Again, we're doing a scale of the metric, so the determinant is absolute value 1. Or we get nil. So these are the these are the unimodular groups that can be expressed as a semi-direct product. And this is a description of all the left invariant metrics on those groups. It's very nice, very canonical. All right. Now, we're only missing the general classification of unimodular groups. We've done the ones which are semi-direct products. So to understand that in general, again, I'm sort of following Milner here. There always exists an orthonormal basis for the Lie algebra, such that these Lie brackets give you structure constants. Okay, notice the order. E2, E3 gives you E1. a constant thing here. E3, E1, sort of cyclically ordered in here. And you get these numbers which are called the structure constants for the Lie algebra. And we're going to talk about simply connected Lie group. The Lie algebra determines the group structure. So the Lie algebra is like understanding the group. We understand the Lie algebra, and understanding the Lie algebra means we know what these constants are. If we know what the constants are, we know the metric, and we know the we're going to know the group structure. Okay. So assume are positive oriented, blah 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 blah. Okay. All right. Okay. So if you choose the orientation correctly, then you can make some choices about the sign of these constants. Okay. Also, if you have a given metric with an orthonormal basis that has this property in a unimodular group, you get all the other metrics by just declaring that some constants times these vectors are perpendicular and length 1. So in the original metric, they're perpendicular of length 1, but now you change the lengths of those vectors, if you want to make them longer or shorter, and declare those to be unit length. That gives you a metric, and also declare them to be perpendicular. So you can't do this in a non-unimodular group, but in a unimodular group you can do this very simple sort of change. You have one particular metric, it gives you one particular nice orthonormal basis, it gives you these structure constants here, and then you get all the other left invariant metrics by saying these are orthogonal axes, but you're changing the lengths of those directions. Okay? So that gives you a description of all left invariant metrics on unimodular groups. And remember, we had even a nicer description when it was a semi-direct product. So that was even more like canonical, more sort of easier to do calculations with. But this is also very easy to do calculations with once you know this sort of result. So what do we have? Then it's just a question of classifying the different signs of the constants to understand what the group structure is. So we have 3 pluses. That gives us the group SU2, which is a bunch of different ways to describe that. The universal cover of SO3, unit length quaternions, SU2. Anyway, that's what we get, SU2. If you have plus plus minus, we get the group structure of PSL2R tilde, the universal cover of the projective special linear group. Plus plus 0, we already saw that before, E2 tilde, that's a semi-direct product. We have sol plus minus 0, we have nil, and we have R3. So notice that there's a comment here that all of these groups are semi-direct products. These are the ones that aren't. These are the ones that are a little more complicated to deal with as far as listing all properties and things like that. Semi-direct products are very simple to deal with. Okay, so there's our classification of that. But notice that some of these are limits of other ones. So for example, this is plus plus, and if I let 2 of the pluses go to be, remember we can change the constants. As we change the constants, we change the metric. Remember, there are 3 particular orthogonal directions, and then we change the lengths of those numbers. If we make those numbers go to 0 on some of the components, then we can get something being 0. So 3 pluses can then go to 2 pluses and a 0, in which case we get all the metrics on E2 tilde. So the limit of these groups that has on this boundary of the moduli space of left invariant metrics here, we have the left invariant metrics on E2 tilde. If we let 2 of the pluses go to 0, we get nil. Here we let one of the 2 pluses here go to 0, we go nil. We have PSL2R that has 2 pluses and 1 minus. Let one of the pluses go to 0. We have on the boundary of that space, we have sol. And on the boundary of sol, we have nil. This is, of course, in one direction. This is on the boundary of this space. So we have, this is sort of a picture which describes, as you change the metrics, the homogeneous spaces change, and we get limit homogeneous spaces and limit related groups. The groups in general become simpler on the boundary. Okay. Now we have the same sort of very beautiful structure, even easier to understand for non-unimodular groups. There it really looks like a interval. Looks like a compact interval. At minus infinity we have Sol. Okay. Remember we have this invariant. Every non-unimodular group has a related metric non-linear. Every metric non-unimodular group has a related matrix associated to it. When you put that matrix in standard form, so the trace is 2, that number associated to the group, which is associated to the matrix, is the determinant of the matrix. Okay? However, if you don't do a homothety to make the trace be 2, then you have to recalculate this invariant, right? So this matrix corresponds to if epsilon is small, to a large negative D. Fix A, let epsilon be small. The D invariant for this is not the determinant of this matrix. You have to divide by, I think, epsilon squared. Okay. Anyway, here, what you get here is D going to infinity for these matrices. And if you let epsilon go to 0, remember this is the general metric we have on Sol. So Sol is on the boundary of, so at minus infinity on the non-unimodular groups, they converge to a unimodular group, which is Sol. Remember, this is the D invariant when you write it in standard form. Okay. If you, then we sort of have the values that are less than 1. When you're less than 1, then the matrix always has 2 real eigenvalues. The characteristic polynomial for the matrix has 2 real eigenvalues, and in that case you can diagonalize the matrix. Okay. Of course, when you diagonalize the matrix, you change the metric. So this is just saying that for that group there exists a diagonal matrix representing the group. Okay, and that can be helpful, useful. Okay, D equals 1, of course, we have D equals 1 and we have hyperbolic 3 space. That's the D equal 1 case. Then we have D bigger than 1, and on the boundary of that space, as we go to plus infinity, then we see E2 tilde is on the boundary of that space. So it's like a compact interval, the compactification of the moduli space. At minus infinity, you have Sol. You kind of go up to 1. 1's a special number. So if you're less than 1, you can represent the group with a diagonal matrix. Those don't give you all metrics, but it tells you what the group structure is and gives you some metrics. D equals 1 is kind of special, and then we have D bigger than 1. Okay. And of course, since we can go get E2 tilde on the boundary, we can also continue a little further and get null on the boundary of E2 tilde. So you can even get that as a limit. Okay. So that's sort of the picture. That's all I wanted to say about the classification of left invariant metrics on Lie groups. Very easy to understand. And if you have this and you review it a little bit, even if you've never seen Lie groups before, it's not too hard to feel like you understand how to do things in Lie groups with left invariant metrics. Okay, so now we're going to talk about some special results about Lie groups. Left invariant metrics. Okay, so I'm looking at a Lie group. I'm looking at a one-parameter subgroup. So one-parameter subgroup just means an R subgroup of the group. Okay, so we have R as a subgroup, like in R3. We can think of an axis in R3 as being a subgroup. Let me actually just come down to this example. It's probably easier to understand. So I'm going to be talking about something called you can read it there, algebraic book decompositions. So just kind of think of the following picture. Look at all planes. Look at this example, probably easier. Look at all planes that go through the z-axis. Look at all the planes that go through the z-axis. Now the z-axis is a one-parameter subgroup. Where's the plane? Here's the origin here. The z-axis is a one-parameter subgroup of R3. And if we look at all the vertical planes that go through the z-axis, those are all subgroups. They're subspaces of the vector space. They're all subgroups of R3. And all these planes meet along this line, the z-axis, okay? And when we have a picture like this in a group, so three-dimensional group, we have somehow foliated by planes that all intersect along a one-parameter subgroup, and these planes are subgroups. We're going to call that an algebraic open book decomposition. So let me go through this again. So we have a Lie group, we have a one-parameter subgroup, and we're looking at a foliation of the complement of the group, complement of that one-parameter subgroup in the group. So we're looking in this picture, if G was R3, okay, then and gamma in this picture is the z-axis, then we have a foliation of R3 minus the z-axis, right? Right? We have foliation by half planes, right? This line disconnects each of the planes into two pieces. Those half planes are the leaves of the foliation, right? Okay, so we have the leaves here, and we want the property, in order to be algebraic, we want, if you take the leaf L theta, and the leaf go around by 180 degrees by pi, we take the union of those two, and we glue in the binding, this curve gamma, this one-parameter subgroup. We want that to be a subgroup. So it's just the same picture as we have in R3, the same picture, okay? Okay, and like I said, so we call the L theta leaf of this algebraic book decomposition. Gamma is called the binding, and H theta are called the subgroups of the algebraic open book decomposition. So the word open book decomposition is nothing more than this sort of property. You take a curve, maybe in a three-manifold, and in the complement of the curve, you foliate it essentially as a product foliation, but it's a foliation with respect to a circle. You have a sort of parametrized leaves that glue onto the curve. Those things are called open books, and all this language comes from the idea of a book. I should have brought a book, but anyway, just my notebook will kind of help. So this is the binding, and you can open up the pages. The pages are like this. So it's all supposed to mean something. The word's supposed to mean something here. So it's like a book. This part would be the binding of the book, where the pages glue together. Okay. Of course, in real life, the book has a two-dimensional binding, right? Kind of. But think of it as a one-dimensional binding, like a spiral notebook, and you kind of open up the spiral notebook. Okay, so that's the definition of open book decomposition, and I'm going to give you some interesting examples of these open book decompositions. So examples. So we have to declare certain subgroups. We have to get one-parameter families of subgroups, which play the role. Remember, we have our H thetas. We have to define these subgroups, and I have to have these subgroups intersect along a common one-parameter subgroup. Okay, so if you take a matrix of this form, we get a related group, right, and a related metric on it. But anyway, focusing more on the group right now. Okay, all right, and this is just a comment. This is sort of a degenerate case when B equals 0. Right? Then the matrix sort of doesn't have rank 2. In that case, this is just isometric to H2 cross R. So that's sort of a special, non-generic situation. All right, so we have our usual basis for this. Remember, we have a semi-direct product. E1 and E2 are basis for the R2. E3 is a basis for the R factor, okay? And we have this property, right? Remember, this matrix comes from the linear transformation, which is taking Lie bracket with E3. So E3, E1 is the first column of the matrix. So we have 1, 0. And the second column of the matrix is E3, E2, which is B, E2. So it's 0, B2, B. So that's the matrix related to the adjoint of E3. Right? We're writing down that linear transformation. Here's the matrix. All right, so we have always a particular nice subgroup, which is the R2 cross sort of 0. We have the horizontal plane. Remember, these always look like the way we usually draw it. Semi-direct product, we have okay, so we have this particular plane, right? We have the plane, the horizontal plane, or the xy plane. That's always a subgroup, right? But we have these other interesting subgroups. So it's not hard to check. If we understand how to do multiply, right? We understand how to multiply elements in the group because it's a semi-direct product of the matrix. Not hard to see how to multiply. If you write down these subsets, so for each lambda, assuming b is not 0, you write down J1 of lambda. So just write down such a subset. It's not hard to check that that's a subgroup, okay? And you can also, this is somehow coming from the 1 part. And we have the 2 part, which is somehow the 0b part. So we get these subgroups, okay? And when b is 0, then you also get some subgroups, except something slightly changes. The J1 looks a little different. Remember, b is sort of a degenerate case. Somehow this exponentiation just somehow disappears because things are more degenerate. Yes? Do you have a question or not? No? Okay. Okay? So anyway, you can list these sort of families of subgroups. A little thought shows, well, what happens as lambda goes to infinity or lambda goes to minus infinity? A little thought shows that these subsets converge to these subsets. So think of infinity as somehow the limit of these subgroups. So these horizontal planes, these other planes are somehow tilted planes. So, for example, I think these, so think of we're getting binding, notice all these, J1, let me just take a look at, J1 should have, right, J1 has the x-axis in it. All the J1s contain the x-axis, right? But when you tilt, so it's a one-parameter family of these subgroups that all contain the x-axis, but some limit of them gives you the xy plane. So if the angle changes, then you end up getting the horizontal plane. So it's natural to compactify these groups and parameterize them by the circle rather than by lambda. All right. Anyway, if you take the first open book decomposition is you take the first collection of subgroups together with our limit horizontal plane, or we take the ones that contain the y-axis, and we take the horizontal plane. So those are 2 open book decompositions, and this I'll let you read by yourself. It's not too important for my talk. This is saying something about uniqueness of describing these things, but I'm not too interested in that. Okay, so we have these 2. Keep in mind we have these 2 open book decompositions, and we want to use these to prove an interesting result. Okay, so the first, in order to do that, I need this transversality lemma, and it's a very general result. It says that if you take any, so I take an immersed 2-sphere in my space. Here's an S2, and I want to have a property that the Gauss map. Okay, so I take the 2-sphere, the Gauss map, the unit normal map. At each point, I have the normal to the surface. I can left translate that to the tangent space at the identity of the group, right? I have a metric, I have a unit normal, I can take left translation. It's usual, what's called left invariant Gauss map. Just translate the normal to the tangent space at the identity, okay? So we're going to assume that this is a diffeomorphism. That's this property right here. Assume the Gauss map is a diffeomorphism. Then we take a subgroup, F. I look at the set of left cosets. So these are, I'm taking a subgroup F. Think of that topologically as being a plane. Okay? I mean, a simply connected Lie group, supposedly, yeah. Simply connected Lie group. And I have this sort of family of left cosets, which you can think as a family of parallel planes. Okay? Then the claim is that if we, so these are left translates of that particular plane. Think of this as like a plane, like the XY plane or something. I'm taking left translates of it. Then notice what this picture looks like. You have a family of parallel planes. It's a product foliation. Well, the planes down here don't intersect the sphere. There's a first one that intersects the sphere. Intersects at a point. There's a highest one that intersects the sphere. That's going to be somehow G0 and G1, or sort of these heights. And the claim is we intersect at a single point on the top and the bottom, and all of the planes in between intersect transversely in an immersed curve. Okay? So how do we know, why is this true? Well, just a little bit of thought says, if you have a two-dimensional subgroup, then its Gauss map is constant, because it's invariant under left translation in itself. If you left translate, take an element of a subgroup, H times capital H is just H, right? You leave invariant the subgroup, so the normal vector of a given point translates over to a left translation of that normal vector. So the Gauss map on a subgroup is constant. As well as if you take a subgroup and take a left translate of it, again, a left translate of a surface doesn't change its Gauss map. So we get all these planes, just like in R3, have constant Gauss map. Okay? So you probably figured it out already, but it's not hard to see what happens here. All right. So we kind of think of these. We have we can order. This is a product foliation, so you can think of the quotient space of these planes is like the real number line. And we have this projection of space, like in this picture, into the z-axis, okay? All right. And, but we have constant Gauss map, right? On these planes, we have, this Gauss map is a diffeomorphism. Wherever this function has a critical point, the Gauss map is either plus or minus the normal vector of the planes, right? Just like in R3. The first time you touch, well, it depends how you orient it. Maybe the normal vector is down. The last time you touch, it's up. But the Gauss map of the sphere is a diffeomorphism. So we're going to end up with one vector down here at a local minimum, a local maximum, and now we can't have any more critical points, because any more critical points, we would have to repeat one of those normal vectors again. Right? Think of it. If you come down like this, then you're going to be tangent to a plane here, and you're going to repeat that normal vector. So I'll have a maximum, a minimum, and another critical point. Then I've counted those intipital points on the sphere more than 2 times. Right? Because the Gauss maps are diffeomorphisms. It's the same sort of thing as in R3. So Morse theory tells us that's just impossible. Okay? We can't have more than 2 critical points, right? Right. All right. So again, you can just take a look at it. It's not hard to see. Okay. All right. Okay. So maybe I'll be able to do this in some detail, and that's probably where my talk will finish. All right. And I'm going to leave the lights on. I probably should have turned them out earlier, but I'll leave them on now because I'm going to use the blackboard a little bit. I'll turn them off temporarily. Okay. So our goal is to prove that suppose we have a space with 2 open book decompositions. Remember, we described open book decompositions when we had a matrix which was diagonal. Remember, we had 1 and B on the diagonal and 0 and 0. We described 2 examples of open book decompositions. So, for example, Sol has these kinds of open book decompositions. Any non-unimodular group with its invariant less than 1 has this property. So we have lots of Lie groups which have these open book decompositions. Now, in such a space, I want to look at a sphere. So now take, let's say, a left invariant metric. Look at a sphere an immersed sphere whose left invariant Gauss map is a diffeomorphism. Then the claim is this sphere must be embedded. Okay? So we're going to use the open book decompositions to prove that if the Gauss map is a diffeomorphism, then the sphere must be embedded. Why is this useful? Why am I talking about this in respect to constant mean curvature surfaces? It turns out that if you have, well, it turns out, I'll put in quotes, that every two-sphere in a simply connected Lie group with a left invariant metric, every constant mean curvature two-sphere has the property that its Gauss map is a diffeomorphism. So we can, in certain cases, we know that spheres, their Gauss map of certain spheres in certain spaces, there is a diffeomorphism. So if we knowing that property, then we want to conclude that those spheres are in fact embedded. So this is going to tell us that in certain spaces like Sol, with left invariant metric, any constant mean curvature sphere is always embedded. We're not going to use Alexandrov reflection principle. Remember, that's a standard way to prove embeddedness for surfaces, is use the Alexandrov reflection principle. However, if we take Sol or one of these other spaces with left invariant metric, in general we have the open book decomposition, but we don't have any planes of reflective symmetry. So this is a substitute. If you can think of it in a certain sense, this is a substitute for the Alexandrov reflection principle. All right. All right. So by our previous thing, we can express the group as in this form for some diagonal matrix. This is not the same metric, but the group. We can express the group with respect to a diagonal matrix. Okay. And if you change the metric, how do you change the metric? You change an you pick a new set of 3 independent left invariant vector fields, declare them to be orthogonal, right? That's how you get things. Well, if you take a change of basis, it's not going to change the Gauss map to diffeomorphism. You're just changing by essentially a linear transformation what the Gauss map is. I mean, not exactly, but essentially. So for all intents and purposes, you might as well assume that the original sphere is a sphere in this space, okay? And its Gauss map is a diffeomorphism. Or you can, I think makes it a little simpler to think about. So let's just suppose that this is the metric that we used, okay? Recall we have these two open book decompositions, and with respect to the first one, we had the x-axis as the binding, and with respect to the second one, we had the y-axis as the binding. Okay, so now I'm going to have to turn the light on. Well, maybe I should read this first. The theorem easily follows from the next assertion, since we can express S as a union of two disjoint disks, which are graphs over the xz plane and so forth. It should have been xz and the yz planes. Oh, right, it's a union of two disjoint, right. All right, okay, so in other words, if you remember the Alexandrov reflection principle, you get a plane of Alexandrov symmetry, and each half of the surface is a graph over its projection to that plane. So we're going to do that same thing without having the plane of symmetry. We're going to express the sphere as two disjoint, sort of what we call bigraphs, two graphs that glue out along a curve. Okay, so let me explain why that assertion does what you want to do. Okay, so the assertion says, okay, so let me draw the pictures. The assertion says that each, if you take the binding, take a binding and you take a left translation of it. So look at all left translations of the x-axis. Turns out that those are somehow all parallel to the x-axis. All these lines in space. And what do we know? We know that those lines intersect always. The assertion here is that those lines always intersect in at most 2 points. So in these planes, we're going to see curves like this in a given plane here, and all of the lines that parallel the x-axis in that plane intersect in at most 2 points. Okay. And of course, one of them is going to intersect in one here, and one's going to intersect in one there. So we end up with, in each plane we have an interval. In each plane we get like an interval. We get a yellow interval and a blue one or a red one. Okay, we get sort of, that's what, if the assertion is true, we get this sort of picture. On each plane we see a curve, an immersed curve, and it breaks up into a yellow and a red piece. All the yellow curves make a disk. And these, remember, see this curve here, the yellow curve, each of these are graphs over that interval. And so you end up with all these curves you project onto the YZ plane in this picture, then you get a yellow disk, or you get a red disk. And then they glue together and make the whole sphere. But you could say, well, maybe this one can intersect with that one. Well, I also have lines in this direction with the same sort of property. So it's a graph in two ways. So these graphs, these two disks can't intersect each other. It's very similar to arguing that you use in Alexander's reflection principle. Okay, so if we prove this assertion, then we're going to be in good shape. So we just need to prove this assertion to understand why the spheres are embedded. So here's the assertion again. So we're going to take the, I'm going to restrict to a special case that I equals 1. It's the same kind of argument. So here's the x-axis, right? So x-axis is our binding. And when we have all these one-parameter subgroups that all are like planes that rotate around the x-axis. That's our picture for the binding. So we're going to do it for I equal 1. Okay, suppose that it fails. Suppose that this contains more than 2 points. Well, if it contains more than 2 points, Sard's theorem, general position argument, implies that there's some curve that intersects in 4 points. Okay? If you have more than 2, in fact, there's one binding that intersects the surface transversely in at least 4 points. So that's what we're saying here. We have at least 4 points in here, and this particular translation of gamma, the binding, intersects the sphere transversely in that many points. Okay? So now, instead of predicting that particular bad situation, let's translate the sphere by A inverse, and now it has the property, it intersects the x-axis in at least 4 points. So we have P1, P2, P3, P4. At least 4 points after translating. We've translated the sphere now, so it's intersecting this in at least 4 points. Okay? But remember that this binding, this curve, lies in all of the subgroups of the open book decomposition, right? So each of the subgroups now intersects also at least 4 points. But remember the transversality theorem. The transversality lemma said that if a subgroup intersects in more than 1 point, it intersects the sphere transversely. Okay? So, for example, the xy plane intersects the surface, whatever, in an immersed curve, right? So if we intersect at least 4 points, we intersect in a transversely in a curve. Okay? So keep, right? In particular, remember L theta is an open subset of the subgroup. So the open subset also intersects the surface transversely. The sphere. It intersects the surface. In this case, we have 2 half planes, right? You get this arc, you have that arc, you have some arcs on those leaves. Okay. All right. So let me try to draw the picture now. We have remember we have a lot of subgroups here. So we have try to draw the picture. Here's the axis. We have all these subgroups which are intersecting. It's kind of look like here's theta going around. Here's the stripe. x-axis like this. That's the binding. And then we have all these planes that are somehow rotating around the axis. Okay. And associated to these planes, we have the unit, not the unit normal, we have a normal field, a variational field for this one parameter family of planes. And that's called partial vector theta. So think of this as a normal variation vector field. Okay, so back in the abstract sphere, we have points P1, P2, P3, P4. And because the sphere is transverse to the foliation, this foliation, the normal projection, where is that? We have it written down here. Right, it's a notation here somewhere, isn't it? Oh, right here. Partial vector theta t. So we're looking at partial vector theta, the tangential part on the sphere. That's a vector field on the sphere, a non-zero vector field. It's not defined at these points, but we know what it looks like around each of the points. Right? If you intersect at a given point here, then it looks like a little disc transverse to that axis. Remember, the binding was transverse to the surface. So it's like a little disc, and there's a little pattern there, which is the pattern of how it intersects the foliation. Looks like little crosses. And then we have partial vector theta goes around these points. Right? It's rotating around these points. Okay? So we have a vector field in the sphere which is non-zero outside a finite number of points, and it's rotating around each of these points. Therefore, the rotation number, or the rotational index, or the Hopf index at those points is +1, right? If you take the rotation this rotation like this is like minus the density function, and it has plus 1 index. So this vector field has a +1 index on the sphere around each of these points. For example, I think you might want to try to understand this little property about the Chico constant. That's sort of a nice thing. This page, you can see the proofs yourself. Okay, something called the Chico constant. So there's a nice theorem here, which I write down the proof for. And then there's a discussion about conjectures. In particular, I give a proof of the Hopf uniqueness and existence for constant curvature spheres in SU2 with respect to any left invariant metric. Anyway, so lots of interesting conjectures, and I'm not going to have time to talk about them. So I think that's probably it for now. I don't know if anybody had any questions.
Are there any questions?